Next set of applications are quite enjoyable. They're using connectedness as a topological property. Okay, so recall, so if x and y are connected, so if x and y are connected and y are homeomorphic, we have an actually stronger statement. So I think it deserves to be called a theorem, though it's a consequence of what we proved earlier. So here's the theorem we use. I mentioned if homeomorphic spaces are either both connected or not, but more than that is true if x and y are connected, are homeomorphic, sorry. Morphic. Then x has the same number of components of connected components. Y. And proof briefly in line. So I should just say idea of proof. A homeomorphism. It preserves connectivity, it preserves inclusion, it preserves everything. So homeomorphism f from x to y gives a bijection on connected components. This is because the image of a connected component is connected, and if you had a bigger connected sum in that, so we have here x and we have here y, and we have this connected component, its image is connected, and if I had a bigger set here that contained it which was connected, its in image under G, well we have f in this direction and G here, we'll give a bigger set here which is connected, but this is supposed to be a connected component, so that's impossible. So maximality is also preserved. So connected components, so both being connected and maximal are preserved, and so connected components go to connected components, and they don't miss out any because otherwise we can look at their image under G. And distinct one goes to distinct ones because it's a bijection. I mean, if they're equal as sets, if the images are equal, then these initial ones should also be equal. So this is the quick idea of connected sum. So how do we use it? So the first example is almost trivial. So 0, 1, let's say this is not homeomorphic to let's say pair 0, 1 union, say 2, 3. Because we can see this is connected, we have proved that. And we have proved each of these is connected. So here we have 2 connected components and one is not 2. So we have different number of connected components. So connected components, so thus, let me state this. We have talked about topological properties. The properties preserved under connected, under homeomorphism. Similarly, number of connected components is a topological invariant, which means if two spaces are the same topologically, that is, they may look quite different otherwise, but they're homeomorphic, then the number of connected components of one is the same as number of connected components of the other. So using this, if the number of connected components is different, then we actually end up saying the spaces are different. This was a direct use, but there are nice ways we can use it other than these. Okay, so let me just note the following. So proposition here is AB is not homeomorphic to AB. And we'll use a standard idea of proof, which we can use many, many times, but since this is the first time, I will sketch it in a little more detail. Okay. So first, so the main idea, we use the following properties. If X belongs to AB, then if I look at AB and remove from it the point X, has 2 components for all X. Okay, because this is just AX for all X in AB. So this is because this is AX union X comma B. These are both open and they are connected. So you have two connected sets. As soon as you have a decomposition into open connected sets, these are the connected components. That's automatic. Okay. So for on the other hand, for X belongs to AB, A comma B minus X. I'm sorry, I want to take this set. For this space, if I subtract a single point, has two components except when X equals the endpoint B, one component. In the other hand, if I delete B, I get one component. So the number of points where if you delete it, you get two components is exactly 1. Now what happens here? So this so claim is we cannot get a homomorphism. So the claim. Okay, we've already claimed that. So suppose f from AB to AB, this one, is a homeomorphism. This is a homeomorphism from now, and we want inverse. G. Now we know we are going to use the fact that restrictions of continuous maps are continuous to say, okay, so let x naught in AB be G of the point B. Okay, then f of x naught is actually B. We know this. So they are inverses of each other. We won't actually use this, but what we can use is we see G restricted to AB. This, if we have dropped B from the map G, which normally has the endpoint, so this is going to map AB to everything itself, its image. Okay, and the image is little ab minus x naught is a homeomorphism. Okay, with inverse, again we can f restricted to ab minus x0, and this is going to map ab minus x0 to AB. So if I drop a point, so I have this half open interval and I have an open interval and I allegedly have a homeomorphism, f goes this way, g goes this way. G has to send it to some point in the open interval, which I call x0. x0 goes back. If I drop these 2 points, I still have a continuous map on the restriction. Because it misses this point, it's well defined, and restrictions of continuous maps are continuous. And we have an inverse, which is also continuous. So it's a homeomorphism. Okay, so this is a homeomorphism. But we have, AB minus x0 has 2 components. While AB has 1, while AB is connected. And this is a contradiction. Okay. So we used, well, we did this directly, but in general we can use the following lemma, which we could have arranged our proof using that lemma instead of this way, and which will generalize to the some more cases. So lemma is that if f maps x to y is a homeomorphism then the number of components for x in X, the number of components of X minus this is the number of components of the image y minus f of x. I could just write this as f of x, but a set here. Okay, because they are homeomorphic. And so similarly, the way in which we'll use it is that for if f maps x and x, if x and y are homeomorphic, x, y are homeomorphic, and k is a natural number, then the homeomorphism has to take points where if I delete x up, these should not be small x and y, I want sets. Okay, then the same logic tells you that if I look at the cardinality of x in X such that x minus this point has k components, whatever k is, that the number of points which if you delete you have k components, is cardinality of y in Y such that y minus the point y has k components. Okay, this is simply because if I look at this set, so let me just write the proof briefly. F, a homeomorphism, gives a bijection between these sets. Between the sets above. Why is this? Because we saw that if we have a homeomorphism, the number of components of deleted point is the same as number of components of the image deleted point. So if I look at any point which has homeomorphisms or bijections anyway from something to something else, okay, to its image, but if I look at those x so that when I delete little x from the space, we have k components, then the image will also have, I mean, if I delete the image, that will also have k components. And since we have a map G the other way, given such a point, it comes from this point. So this gives you a two-way, a bijection between these two sets. Okay. So with the setup like this, we note that, so the following proposition, again an example. Okay, there will be other ways of proving this, but AB is not homeomorphic to, let's say, the half open interval. Namely, if I look at the proof, cardinality of, so let's call this x, and this is y. So if I look at cardinality of x in X, such that x minus little x has one component. Well, what are the points where if you delete them you have one component? Either end point. This is 2. But if I look at the cardinality of y in Y in the half open interval such that y minus x has one component, this cardinality is 1. Okay, so it's a little bit careful because this is true. This is the first time we are using this kind of argument, but it's a very useful way to use it. You have to be a little careful here, not so much in set topology, but when you look at homotopies, because set differences don't behave well with respect to homotopy. But we have found a powerful way. It's not just that we count the number of components, but we see that if we delete a point, what happens to the components. This can be refined in a lot of ways. We can look at local connectivity, for example, which we won't talk about here, enough to characterize the real line. Okay, so here's another example which is interesting. Okay, so proposition is S1 is not homeomorphic to any interval, an interval. Why is that? That is because S1 minus X0 is connected for all X0. Okay, we come back to this in a moment because we are going to use a following theorem. This is important, and we'll use the same argument for S1 as well. R is not homeomorphic to Rn if n is greater than 1. So R is not, line is not homeomorphic to R squared. Okay. So as I commented in another context, this is the sort of statement that was regarded as absolutely obvious. But then the space filling curves came along, and it seemed equally obvious that there can't be such things as space filling curves, because the problem is Rn is bigger than R. So when you look, so from a smaller set to a bigger set, you can't have a surjection. It's not the injection part that is a problem. That's what the intuition would say. But we do have surjections in both directions. So that makes the whole thing more subtle. So we need some other way to prove it. And here the point is that R minus X, single point, is connected, is not connected for all X in R, but Rn minus X, so whatever point we took, is connected for all X in R. It's quite easy to see that it's connected. We'll see it via path connectivity when we come to that later. So given any 2 points, we have a path like this. So that's a connected set that contains both these. So if this is the point X that is deleted and I take 2 different points, I can join them either by a line, or if we are unlucky and the line passes through X, by 2 lines. So I might as well say it in words. So this is what we'll call path connectivity. But from what we know, we can find a function from the interval to Rn minus this point X, and which will begin at A and end at B. We know the image of an interval is connected. So A and B are connected. A and B are in a connected set. But we had already commented that if every pair of points is in a connected set, the whole space is connected. Okay. And finally, the last example in this series is how about Rn and S1? We see S1 also doesn't get deleted. Rn is not homeomorphic to S1 for all n greater than for all n, but let's say greater than 1. Okay. NS1 is already done. S1 is not homeomorphic to an interval. Let me clarify that proof. If I took an interval, the number of points which you could delete and it remains connected is either 0, 1 or 2. But for S1 it's every point. So it follows that S1 is not an interval. But here, just deleting 1 point won't do, but you can probably think of the idea, which is you delete 2 points, namely S1 minus xy is not connected for all xy in S1, but Rn minus xy in S1 where x is not equal to y, but Rn minus xy, if I remove 2 points from Rn, is connected for all xy in Rn. And again, x is distinct for I for all distinct points. So how does this formally prove this? If I have a function f from S1 to Rn, which is a homeomorphism, I'll take 2 points, and then their images will give me some pair of points here in Rn, 2 points. The complement of these is homeomorphic to the complement of these points. But the complement of this has two components, while the complement of this is connected, which is impossible. It's the same argument we used before, except this time we have 2 points deleted. But even if I delete 2 points from Rn, it is easy to find a path from any 2 which avoids both these points. And in fact, any finite number of points deleted from Rn within at least 2 is going to leave a connected space. So we've seen we can kind of leverage this idea of connected components as a topological invariant, together with the idea that given one space we can construct other associated spaces. Namely, we have, by deleting a point, deleting 2 points and so on. These depend on choices, but you vary over the choices or quantify over the choices to claim that things are not homeomorphic. So we have found a nice way. This is really zero-dimensional algebraic topology in a sense. Higher dimensional will have to wait for an algebraic topology course, but still we have seen nice examples of spaces which are not homeomorphic to each other.